Hey, it's Horner. We're going to talk about 17.2 electric potential. Electric potential, or voltage as we commonly know it, is really just the electric potential energy, which is UE, per unit charge. So if you have a charge and you know the potential energy, you can find the potential for that unit charge, and we call that electric potential. And it's often, we shorten that to just say potential itself. Here's a kind of a little bit of a help. This side of the or this lead will have a positive charge on it. This lead, sometimes we call it a plate, will have a negative charge on it. And notice that the positive side is high potential and the negative side is low potential. So for our positive charge here, this high potential is on the side where the positive plate is. But for the negative charge, the high potential energy for this negative charge is actually on the low potential side because of the way we define potential. So that's really important to kind of notice as we go through this unit. They don't really have a direction in space. They're just added like any other scalar. They can be positive or negative. Even though they don't have a direction, they can be not positive or negative, and so we have to add them with algebraic signs. And if we have, if the potential at a point due to a collection of fixed charges is V, then we can write the charge Q. Then when we have charge Q, the potential energy is Q times that potential. So really easy equation to work with. If I want to know what the change in the potential energy is, then the easiest thing for me to do, here I'm going to go back a slide, is just look at the change in potential. So if I go from point A to point B, this is my final point, my original point, subtract the two, that gives me my change in potential, take that times the charge, and that gives me my potential energy. And so those are your equations that you're going to use a little bit. Once again, we did say that for a positive charge, lower potential energy means lower potential, so low PE means low potential. But for an electron, high potential energy means you're on the low potential side. So that's kind of a confusing thing for some people, but as long as you remember positive, high, and high, and then we know negative on the high side would give us low potential energy, and negative on the low potential side gives us high potential. So just think kind of about how they would move. For the next part, there's a pretty important thing here that just says that the electric field points in the direction of decreasing potential. So we know that for that plate, if I have a positive plate here and I have a negative plate, the electric field always goes from high potential to low potential. And so we always go this way, and that would be the direction of that electric field, which is a scalar because it does have a direction. For the next part, we're going to look at example 17.3. Here we've got a battery-powered lantern. It's switched on for 5 minutes. During that time, electrons with total charge of 8 times 10 to the second coulombs flow through the lamp, and 9,600 joules of electric potential energy is converted to light and to heat. They want to know through which potential do the electrons move. So let's take a look at this first part here. So we have the equation change of potential is equal to the charge times the change of potential, and we can apply that equation to a single electron, but since all the electrons move at the same one, we can just let Q be the total charge. So when we solve this one, we basically are just going to divide. So here we've got the change of potential energy. Remember, energy is measured in joules, divided by negative 8 times 10 to the second coulombs, and we end up with a positive 12 volts. And remember, volts is the change in potential. Volt is also equal to a joule per coulomb. So this unit is a joule per coulomb. We really want to make sure we try to simplify it down to volts whenever we can. The next part of this unit is talking about that potential energy due to just a point charge itself. So if that charge Q is close to another point charge Q, we know that that electric potential energy is KQQ all over R. So if we are looking now at potential, electric potential at a distance from a point charge, now we've got V is equal to KQ over R. So we just we've removed that Q. Here we're assuming that voltage is 0 at a very, very high radius or distance between the two. If I have several different charges and I want to take a look at all of those, I can say that we can use superposition to look at the potential. So the potential at point P due to several point charges is the sum of all those potentials due to each of the charges. So this is very similar to if I have several things lined up, several different charges, and maybe I have +2 and I have -1 and I have +3. And if we're right here, if we want to know what is the potential at this point, we can use that superposition principle in order to find it. So here's a good example. I've got charge Q1 is right here. It's 4 microcoulombs. It's located at 0,3. I've got another one which is positive located at 1,0, and then finally the last one which is -3 microcoulombs, and it's at 2,2. So they want us to find the electric potential at point A. So that would be right here due to the 3 charges. And then they say a point charge of -5 nanocoulombs moves from a great distance to point A. So that means that we've had it way over here, -5 nanocoulombs, and it moves from here and then moves to point A. They want to know what is the change in electric potential energy. So to find that change of potential energy, first thing we need to do is determine the distances from the different charges to letter A. So here's R1. This is the, that's R1. And that's the change of position from Q1 to A. So notice it's only 2 centimeters. If I want to do Q2, so I want R2, that's this distance. That's the square root of 2 centimeters. So square root of 2 centimeters would be to R2, and it's because I've got 1 centimeter here and 1 centimeter here, so 1 squared plus 1 squared is 2, and then I would just use R squared is equal to 1 squared plus 1 squared, so that's 2. That's where you end up with R is equal to the square root of 2, and that's 1.414, and then finally we have the position change from here to here, so we're going to do 1 in the vertical and 2 in the horizontal, and we want to know this line, so if we do 2 here and 1 here, that's the 1 squared plus 2 squared, so square root of 5, and that gives us 2.236. So we're going to use our equation. The potential is equal to K times the sum of all the charges divided by all the radii. So let's go ahead and take a look at the next part. We know that the K value is just 9 times 10 to the 9th. We've put each one of our charges in and then the distance to the position in question. If you go ahead and do your math, you should end up with positive 1.863 times 10 to the 6 volts. And that's your answer for A. For part B, they want us to find that potential energy change, and so we are basically going from 0 voltage to the voltage that we have. We're going to multiply that times RQ. So here's our charge, and then there's the voltage we just came up with. And remember, at a very far distance, V is equal to 0 when your radius is equal to infinity. And we end up with a negative 9.3 times 10 to the negative 3rd joules. And that would be our change in energy for 17.4. For 17.5, it says we have 4 equal positive point charges. So here they're all equal at fixed corners of a side S. They want to know, is the electric field 0 at the center of the square? So they want to know, is the electric field 0 at the center of the square, and then is the potential 0 at the center of the square. So let's go ahead and take a look at each one of these. We know the electric field at the center is the vector sum of all the fields. And so the figure below here shows the electric field for each one of those charges coming from the center. And so because each of these vectors have the same magnitude, because they're all from the same distance to each one of the charges, and because they're symmetrical, Everything here is 90 degrees. They all have the same length, so these cancel each other, and the vector sum of the electric fields is 0. So the electric field at the very middle of the 4 charges is 0. So E total would be 0. For letter B, the potential is a scalar rather than a vector, and the potential at the center of the square is the scalar sum of all those potentials. What we need to do is we need to look at that potential, and we know it's 4 times K times Q all over R. And so each one of those charges is positive since Q is greater than 0. And the total potential at the center of the square is going to be what we've kind of just alluded to here. And whoops, so I'm going to go back one more time. And so what we'd have to do is figure out what that position is, S, and then divide that by the square root of 2, and then we'd be able to plug in our 9 times 10 to the 9, and then whatever our charge is, and that would give us that. So here the center, the potential, would not be 0. It would be some number above 0 itself. And that was example 17.5. So if we look at potential due to a spherical conductor, so something that's circular here, we saw that in 16.4 the field outside that charging sphere is the same as if all the charge were concentrated in a point located at the center of the sphere. So the electric potential due to that conducting sphere is similar to the potential due to that point charge that we saw. So a couple of graphs that we can look at. Here is the electric field inside of that conductor. So essentially what you've got is you have a conductor who the center of itself, here this is radius. So we could kind of look at, if we just look at the sphere itself, we could kind of do like this. Inside, we would not have any electric potential, and then on the outside it would be very, very large. So remember, all those charges tend to congregate on the outside. And then you'd have a really high, and then as we go away, remember that electric field is 1 over R squared. Same thing kind of happens here for voltage, but for voltage on the inside of the sphere, our voltage is just as it is on the very outside. So our potential on the inside is exactly the same all the way across. But then once we get outside, we notice that that starts to dive off also, but it dives off as 1 over R and not over 1 over R squared. And so there's the difference between the electric field and the electric potential between the two. The potential is chosen to be 0 for R is equal to infinity. So the electric field outside of the sphere is the same as the field at a distance R from the point charge. And so we just kind of showed that a little bit. And so we have an equation here. We just said the voltage is equal to KQ over R, and at the surface of the sphere, that potential should be KQ over R. And really, all they want to show you here is that the little r here is the distance from that point charge. Okay, and we know that we've got from here to here is that radius. So it's the same all the way across. So at the surface of the sphere, that potential is the same. So it's a little bit confusing. It's a little bit easier to see, I think, when we actually take a look at this picture where we're looking at, it doesn't matter where you are inside that sphere, that potential is the same until you get outside the sphere. And then it decreases as proportional to 1 over R. Since the electric field inside that cavity is 0, there's no work done by the electric field, and therefore the potential anywhere inside the sphere is the same as what it is on the surface. So they've just spent about 3 slides going through the same thing, just trying to say that, hey, you know, inside the sphere we're going to have the same potential as we do just right at the surface of the sphere. So that's really all we're looking at. A Van de Graaff generator, you've seen those in action. This is kind of how it works. We've got a source of charge. That conveyor belt will actually, there's a belt on the inside that transfers that charge up, and then that conducting sphere on the outside, which is metal, allows that charge to kind of sit on the outside. The uncharged belt then returns, comes back, picks up the charge again, and then it's basically just depositing it on the outside. So it's kind of like you've got somebody, you give them a bucket of paint, they go up and then they paint the outside, they run out, they come back down, they pick up more paint, come back up again is essentially how you can think about the Van de Graaff. So here in example 17.6, I want to charge a Van de Graaff to 240,000 volts. And that's kind of what we said that ours was probably at least on a really nice dry day. On a day with average humidity, though, it's only about 240. So we said ours was closer probably to 400. There's an electric field of 8.0 times 10 to the 5th newtons per coulomb. And if it's that large, it ionizes air molecules, and then the charge is allowed to leak off the Van de Graaff, and you can kind of feel it. They want us to find the minimum radius of the conducting sphere under these conditions. So we want to know how big is that ball supposed to be on top. So our strategy here is basically just to set the conducting sphere equal to Vmax of 240,000 volts and require the electric field just outside the sphere to be about 8 times 10 to the 5th. So since both the electric field vector and the potential scalar depend on the charge on the sphere and its radius, we're going to be able to eliminate the charge and just solve for the radius itself. So here's our two equations. This is for potential. This is for the electric field. We can see that if we have E is equal to V over R just outside the sphere, and if we let V equals V max and make sure that that electric potential is less, I'm sorry, the electric field is less than the maximum electric field, we can find that we have this relationship where the radius should be greater than the maximum voltage divided by the maximum electric field. And so we just basically are just dividing the two. When we do that, the minimum radius of that sphere that we have with all the charge on the outside should be about 30 centimeters or 0.3 meters. And so when they build these, they kind of try to do that, make sure that they're the right size. So the bigger the sphere, the bigger the field you're going to have, and the more voltage you're going to produce on those. So it's really kind of just dependent on about how big that sphere is as to what's going to happen. For the next slide here, I think I'm stuck. All right, so for the next slide here, we've got potential differences in biological systems. So if you look at a cell, the inside and outside of a biological cell are not the same in terms of potential. So there is a potential across the cell membrane, and it's because you have different ions and different fluids inside and outside of the cell. And so they're really important in both nerve and muscle cells. So we want to make sure we can transfer information and then use that information in order to get those cells to fire. So we talk about action potentials. That is really just about potential energy. Remember, your nerves, when they fire, we're looking at millivolts here, so we're not looking at actual volts themselves, but we're looking at a thousandth of a volt. So this would be 50 millivolts, and we're going from somewhere about negative 80 or so all the way up to that positive 50. So when a nerve fires, you get a pretty big change in potential, and then when it comes back down, we notice that our average line here is where that resting potential is. So here we've got a nerve impulse, and then that nerve kind of relaxes a little bit, and then it gets charged up again, gets ready to go. That's your application for nerve impulses. There's a lot of different things that rely on electric potential, so electrocardiographs, electroencephalograms, and electroretinographs. Graphs. These are really, really important. Cardiographs for the heart, encephalograms for the brain, and then retinographs for eyes. And an ECG measures all the potential difference between the points on the chest. So if you've ever been hooked up to an electrocardiogram machine, you kind of know what that is. But then you see all of those blips, doink, that come up, doink, and go across. And we're really just looking at potential differences here. And so you'll go from some sort of negative potential, some resting potential, up to the positive and the back down. And we just use electrodes on the skin to do that, which is really kind of really nice. So here's that again, and you can see that potential change. it's amplified so that we can see it a little bit better. But that's basically what you're doing in all three of those, is just looking at the potential as it goes through. Next time we'll take a look at equal potential surfaces.